understood the field of brittle shear zone, ductile shear zone and transition zone. Now, suppose you take a cross section across Himalaya. So this is Himalaya. You are able to see na from that angle. Top part of Himalaya. So, first 10 kilometer will brittle. First 10 kilometer will brittle. Then ductile brittle transition will start. Then ductile will start. Say 15 kilometer. This is how the zones are distributed. Now, this mountain belt is produced from a compression. China and India block, they have pressed and developed this mountain belt. Then what type of structure? Fault will develop here. If there is a horizontal compression like this, so you will get thrust. Because as you know, this acute angle will face the direction of compression in the brittle. So you will develop thrust here. Let us draw a thrust like this. So this angle is 30 degrees. Very low angle thrust will develop, fault will develop. So this part will go. You understand this thing now? If this is horizontal, this angle will be nearly 30 degrees. This is horizontal. Why? The direction of, so this one is developed, this part. This thrust is developing here. Now, if you go to this zone, ductile zone, the ductile zone same thrust, will become steep like this. Why? In ductile zone, this angle will become this way, convex. Here is acute, here is obtuse. So obtuse angle will face the direction of compression. This is what we have observed in our circle. So now same thrust, will become like this. As you go down, the surface you will get a very gentle thrust, but if you go down, this will become a very steep thrust. You understand now why it is changing its nature from a, so as one goes down, a low angle thrust becomes a steep angle thrust. Steep angle ductile thrust. Here is a brittle thrust. This part is clear now, because this is the principle. If the rock is brittle, the acute angle should face the direction of compression. The material is ductile, the obtuse angle should face. Yeah. See, this you can explain, with the help of this Mohr envelope. Mohr envelope will take a turn like this. Yes. So in the compression zone, the circle is like this. So this angle is 60 degrees in the compression. But if you go to ductile zone, the circle will touch this side. So this angle is 120 degrees. But if you stay here, in the transition zone, the circle will be here, touching here, like this, 90 degrees. 90 degrees. So these are the 2 theta values. 2 theta values. So here it is 30 degrees, here it is 45 degrees, here it is 60 degrees. Here, understood this pattern. This is very important observation you should remember. Now, I remove this part. Suppose you are working in Aravali or Eastern Ghats, Southern India, South India granulite belt. So these are the areas where you are working, suppose, and you found a thrust. You found a thrust there. So what should be the deep angle? Suppose you found a thrust. So that means your Aravali, Eastern Ghats and South India, they are at the present level of exposure. Where it is, they are all Precambrian mobile belts. They are Precambrian mobile belts. Himalaya is a present day mobile belt, tertiary mobile belt. Now, but these are Precambrian mobile belts. So Precambrian mobile belts means what? Initially they were like this. By now everything has been eroded away. Everything has gone from its top. So Aravali has left this amount, Similarly, Eastern Ghats and South India, this part of those mobile belts, have been removed by erosion. You are seeing this part. The present day exposure, that is somewhat was telling Singhum shear zone. Similarly, terrain boundary shear zone in Eastern Ghats. Very important shear zones are there. Go to South India, Palghar Kaveri shear zones. They are all thrust. But what should be the deep angle? 60 degree, 70 degree. Because you are seeing this part of the thrust now. But Himalaya, in case of Himalaya, you are seeing this part. Himalaya is a recent mobile belt. Now, the top part is still there. So if somebody asks you Himalaya, you will be seeing this part. But if you suppose somebody says Aravali, you are seeing this part now. This part has gone out. In Palghar also. Everything has gone out. So this low angle fabric you will not see in case of Palghar, in case of Eastern Ghats, in case of Singhum, Satpura, nowhere you will get this part. This part is exposed. That is why suppose somebody says Singhum mobile belt, the thrust is so steep. But in Himalaya, why it is low angle? In Himalaya you see the brittle part. So it is low angle. But in case of Singhum you see the ductile part. That is why it is steep angle. Understood these things now? I will write down this point so that you will not forget what he says. In case of Himalaya mobile belt, it is a tertiary mobile belt. Tertiary means recent, tertiary mobile belt. So the brittle part is still existing. Brittle part is still existing. Brittle part is still existing. Hence, the thrust are low angle. Low angle. You must have read in your MSc days. You have MBT, then you have MCT, then Southern STD. These are thrusts. What is the angle? Or 30 degree, around 30 degree inclination. Because you are seeing this part of the crust in case of Himalaya. So examples are your MDT, main boundary thrust, main central thrust, southern Tibet thrust, southern Tibet detachment. It's a very low angle. But if you go to, I will remove this part. If you go to Aravalis or Singhum, in case of Singhum, Aravali or Eastern Ghats, in this case what happens? The brittle part is removed. Brittle part has been removed. Over the years, by erosion and extension, this part has gone. So you are seeing the ductile part is visible now. Ductile belts are visible. Exposed. Ductile belts are exposed. Hence, rocks are steep angle. Understood ना? So कभी कोई क्वेश्चन आए तीन गुण सी होती है. What should be inclination 60 degree, 70 degree. But MBT cannot be 60, 70 degree. It will be 30 degree, 20 degree, like that. Okay. Now, see, you understood now, no? What is this? What is the difference between these two? So one is a fault, another one is a shear zone. Just for use sake we are using these terms. Otherwise this is a brittle shear zone, that is a ductile shear zone. Now this is a sharp cut. So sometimes this becomes a zone. It's not a single plane. This is a fault zone. Maybe some few meters, centimeter to meter thickness. Similarly here also it is a ductile shear zone. From ductile shear plane to ductile shear zone. Now in this case, this zone will be marked by what? Kata classes. Kata classes is the mechanism. The rocks are being crushed. In this case, it is a crushing. Crushing is the main mechanism. Just like we crush materials like rice, wheat. Similarly, this material, the rock is being crushed here. Rock is being crushed. That is the technically it is called kata classes. Understood, na? So this crushed material is called a process is called kata classes. The product is called kata classides. T comes in. Kata classides. So kata classides will have angular fragments like this, because this is a mechanical grinding you are doing. Mechanical grinding the mechanical grinding you are doing, and there will be very fine grained powders. Very fine grained powders here and there. So this is the rock, known as kata classides. Angular fragments set in a fine grained matrix. That is how kata classite will be identified. So these are angular clusters, angular fragments. Angular fragments is called angular clast. Clast, C-L-A-S-T. It has a name called brachia. You can say it is also brachia. Sometimes the clasts are little rounded also. When you say conglomerate, depending on the shape. So brachia are angular, conglomerates are rounded. Roundeds are very rare. Otherwise brachias are more common. So this group name is your kata classides. So kata classides is a fault rock identified by this angular class set in a fine grained matrix. Now depending on this class to matrix ratio, you understand what is a class, what is a matrix. So you can have 90% class, 90%, around 50%, around 10%. You can have a proto kata classite. Here is ultra kata glassite. Central one you can say simple cataclasite. Some people say orthocataclasites also, but simple write cataclasite. This is a protocataclasites where the class are dominating. If matrix is dominating, ultra cataclasites. Understood na? Now, see sometimes what happens. The rate of sleep is very fast. Sometimes, not always. So you can say strain rate. Now how fast the material is sleeping like this? How fast? That is the rate of sleep is so fast, you know, very high. So lot of frictional heat is generated. You understood this part now? If it is a slow motion, heat will not generate. However, you know, stress difference, maybe if you are moving very slowly, it will not produce any heat. But you can also feel this difference, you know. You must have seen a matchbox. Matchbox को आप धीरे लो ऐसे, it will not put fire. But when you make it, only fire will come, you know. So this is a fire producing process, you know. Frictional heat is generated. When it is very fast, the rate of sleep is very high. Then rock is melted. Because of this frictional heat. So maybe heat may be above, you know, 1000 degrees centigrade. Very high frictional heat. For a very short time. It cannot stay for a long also, you know. Very short time. So rock is melted, you know. So to produce a melt, which is known as pseudo-tachylite. What is a tachylite? Tachylite is a glassy rock. Glassy what? Basaltic glass. Dark glass. It's called a tachylite. So it will be appearing like this, you know. If you see a thin section, the whole thin section will be looking dark with small plagioclases, you know, here. Plagioclase. This is a glassy basalt. Basalt is fine grain. You will get many grains here and there in case of basalt. But if it is becoming glass, then leaving aside few crisps, the rest of the ground mass is dark. Glass. This is glass. Glass has no structure. Huh? It is absolutely amorphous. So this is called tachylite. So the basalt produces when there is a volcanic eruption. The basalt comes out, you know. It is not yet crystallized. Still melt is in amorphous form. And suddenly quenches. Suddenly it becomes solidified. That produces a glass. So this is a glassy basalt known as tachylite. So here, this is not a basalt, but it is appearing like that, you know, appearing like tachylite. So a pseudo-tachylite will be appearing like same manner like this, you know. You will have a glassy ground mass. This is the glassy ground mass. Glassy ground mass in which there will not be any phenocryst like this. There will be clasts, you know. These angular clasts which I have told you, know. 1, 2, 3, 4, like clasts will be floating here and there. The surrounding mass, which I told matrix, that is a glass down. This is glass. So what happens when the rock melts? Your original material was like this. You had the clasts here and there, and the rock melted. So this melt inverts. The melt inverts, and what? Sudden cooling is called quenching. Sorry. For a long time. Suddenly, because Otherwise the rock is full. Outside this side the rock is full. You are heating this part of the fault, the very high heat. So only this small portion is heated and melted. So when they come in contact with the cold rock, suddenly it quenches. Suddenly it becomes glass, solidifies. That is why a glass is produced. And the remaining those glass which are not melted, they remain floating with this glassy ground mass. So this is called a pseudotakelite. So what is the difference between pseudotakelite and takelite? Takelite is a basaltic glass, whereas pseudotakelite is a fault glass. This is a glass produced in a fault because of high frictional heat. High frictional heat. Remember, frictional heat. So in due course of time, this glass is devitrified. So if you have a pseudotakelite, ET I am writing, pseudotakelite. So little small devitrification, because of devitrification, crystallization. Devitrification results in small crystals to develop in the glass. Small crystals develop in glass. So those small crystals are known as microlights. So this glassy ground mass converts into a mesh of microlights. So depending on the extent of devitrification, the amount of microlights will vary. Depending on the degree of devitrification, devitrification what you understand, na? Crystallization from a solid material. So degree of devitrification will tell how much microlights will be there. We have any photograph here? So understood, na? So it is only when the sleep is very fast, strain rate is very high, the pseudotakelites will be produced. Understood, na? But it is a slow movement, pseudotakelite will not be produced. Now, fault also creates earthquake. Understood? That is what we have seen also. Probably the strike slip faults and the thrust. These are the two faults which creates earthquake. Now what I am telling you, this also creates earthquake. Strike slip and thrust. Normal slip does not create earthquake. Now, same thing also you can think. Fault can also move very slowly. Fault can also move very fast. Just like pseudotakelites are produced because of fast movement, similarly with the earthquakes, so fault creates earthquake, but if the movement is not very fast, it will not create earthquake. Very slow movement, will not create earthquake. If strain rate is very high, then only earthquake will produce. Suppose the rock is there, sudden break, then only earthquake will produce. But if it was just creeping, very slow movement, it will not release the energy, So that is why where there is a fault creating earthquake, seismogeny, it is not only strike slip fault, necessary to create a earthquake. It is strike slip fault with rapid movement. Strain rate very high, then it will create an earthquake. So those strike slip faults are seismogeny. Or a thrust which creates very fast movement, then only it will be seismogeny. Follow this point. Na? So second is your pseudotakelites. Similarly, if the movement is very fast, then pseudotakelites will be produced. Frictional heat will be generated. That is why the pseudotakelites are indicator of Paleoseismicity. So pseudotachylites, you understood this part. Pseudotachylites are paleoseismic indicators. You understand this part or not? How they are correlated. Suppose in an area you found some pseudotachylites. Say that because of this or during that time, the earthquake was happening. Faulting is taking place every day, but earthquake does not take place. Only when there is a rapid movement, earthquake will take place, and that time also pseudotachylites will be generated. So if you find a pseudotachylites in some mobile beds, old pseudotachylites.
Sir, lineation can be produced earthquake.
Which one?
Lineation.
Lineation. No, lineation means what? Lineation is a linear feature. Slicken sides. Slicken sides is a lineation. It is not a genetic criteria for developing a earthquakes or seismic. Out of earthquake, lineations are produced. Because when there is a fault movement, earthquake will be produced and lineation will be also produced. Lineation, you understand what is a lineation? Lineation is a linear feature. Due to movement on a fault plane, these lichen sides or the lineations are produced. Because of movement. Because of the movement also earthquake is produced.
Small magnitude.
Small magnitude. So lineations cannot create earthquake. So when earthquake happens because of fault movement, lineations are also produced. Earthquake is also produced. You follow this point? Now, so that is the relation between the pseudotachylites and the seismic faults.
Pseudotachylites are found in ductile erosion or brittle?
No, you cannot find in ductile erosion. That is what we are doing now. When you go to this place, this will not happen. And rapid movement, fire creating. कभी आप दिया जला को गला कर दीजिए. कभी match box is suppose during rainy season you cannot use a match box. Why? उसका पेपर गिला हो गया. Like that, you cannot create friction. Friction will be only created if it is dry. भाई फुटबॉल खेला आपने ड्राई लैंड में कितना लगता है, इसलिए बारिश का सीजन में फुटबॉल खेलते हैं. ये लागेगा नहीं करके, समझा कि नहीं समझा? So you need to have a dry surface, Ductiles are not dry, na? Soft, na? You cannot create friction out of it.
Find out the composition of pseudotachylites.
Competition.
Composition.
Yeah, you can find out. You just take it, put it in X-ray, XRD.
What is generally the composition?
It's the same rock, the rock which is being faulted, that will produce the melt. The melt is produced from here, na? So that will be same composition. Silica will be there. Generally, granite decomposition. If it is a granitic melt will be produced. If it is a basalt requires very high temperature to produce pseudotachylites.
The brittle shear zone will occur within 10 kilometers.
Within 10 kilometers.
That's the upper crust.
Granite.
Yes.
Say it is a granite.
Then why pseudotachylites? Tachylite is only because of basalt.
That will be pseudo. Appearing like a tachylite. Pseudo means what? Pseudo means false. It is a false tachylite. Appearing like a tachylite. Understood ना? आप पढ़ा होगा ना pseudomorph. Calcite का pseudomorph. It is looking like calcite but not calcite. Similarly, pseudotachylite looks like tachylite but not tachylite. Though it is ground mass is glassy, but this, you see the clasts will be there. Quartz feldspathic clasts, parent rock clasts will be there. But in case of tachylite, the plagioclase phenocrysts will be there. They are not clasts. That is why it is called a pseudotachylite. The name came from here only. Tachylite से name आया. आप दोनों hand specimen देंगे तो you will not be able to distinguish. Both are looking dark, very fine grained aphanitic rocks. You cannot distinguish. So you have to have a lens or microscope. I will show you tomorrow two different photographs. Understood that? So it generates a lot of heat. I told you 1000 degree centigrade heat, is generated very high. But you just go this side and this side, no heat, very cold. that means very highly heated liquid is in touch with a cold country rock. That is why it quenches, suddenly quenches. So glass is produced. If you leave it for longer time, it will not quench. It will crystallize. But you are not leaving it. You are bringing it in touch with the cold rock. So it suddenly quenches. That is why the glass is produced. If you want to know the composition, you take a powder and put in XRD. XRD will tell you the composition. Or make a whole rock analysis. That is Bhuvan is doing all this work. Now, understand the meaning of pseudotactylite. So, lot of work is being done, on pseudotactylites. They are entering as a vein within the fractures. So, how to find out? Suppose, what is the amount of slip along the fault plane that can generate some definite amount of pseudotactylites? Because they are related. Amount of melt will generate depends on the amount of heat. Amount of heat depends on the strain rate, how fast it is being produced. So all these three can be correlated. How much pseudotactylating material is there? What is the heat? How much heat is generated from? And that heat, how much sleep has taken place. All these things have some formulas in equations. So you can find out how much sleep has taken place along a fault plane to generate such pseudotactylates. So those are being done. Okay. So now we will go to ductile shear zone. So never confuse pseudotactylates occur in all shear zones. Only fault brittle shear zones where the rate is very high, the pseudotactylates will be. Otherwise it will not happen. Now let us go to ductile shear zone. So this is your picture. ऐसा. So this part, understood na? So here rock is not crushed. So what type of deformation has taken place? Ductile deformation has taken place. That is what na? So there won't be any angular fragments because the material is ductile condition, soft condition. So the deformation will be by slip, or you can see intracrystalline slip. Intracrystalline. So you have read earlier slip planes.
सर क्रश तो होते हैं सर.
कैसे क्रश होगा?
सर कोई टनल बना रहे हैं, सीयर जोन में क्या होता है, वो बिल्कुल क्रश्ड होते हैं, अनकंसोलिडेटेड होते हैं.
वो कौन से जोन में आप बैठे हैं? ब्रिटल की डक्टाइल. टनल कहाँ बनता है? टनल तो ब्रिटल में बनता है. आप अभी टनल करेंगे 10 किलोमीटर नीचे, कौन टनल करेगा? ये तो सरफेस में पहाड़ जैसा अपना कल्याण जाने का रास्ता है. वहाँ जो भी सीयर जोन होगा तो फॉल्टी होगा, तो क्रश्ड मटेरियल निकलेगा, उससे पानी भी निकलेंगे क्योंकि मटेरियल इज वेरी लूज ना. ग्राउंड वाटर प्रॉब्लम बिकम्स अ ग्रेट प्रॉब्लम इन टनलिंग. बट डक्टाइल shear zone कहाँ है? 10 किलोमीटर बिलो. यू कैनॉट सी इट ऑन द सरफेस नाउ. सो इसलिए आपको यू हैव टू गो टू अरावली, ईस्टर्न घाट्स और साउथ इंडिया बिकॉज दोज रॉक्स आर एक्सपोज नाउ टू द सरफेस. बट हिमालय में आप जाएंगे तो शायद आपको मिल पाएगा. यू विल नॉट गेट डक्टाइल shear zone in हिमालय. So you have to go to this Precambrian mobile belt to see the ductile shear zones. Understood now? So these ductile shear zones, they do not deform by crushing. So cataclasis is not the way the rocks deforms. It is rather by flow. Understood? So this is called, the process is called myelometallurgy. Myelometallurgy. It is opposite of cataclasis. Cataclasis है ब्रिटल में, इधर myelometallization is the process. Rock becomes a myelonite. Their rock was becoming a cataclasite. Here the rock is called a myelonite. So suppose somebody says in myelonite, what is the nature of deformation? Intracrystalline slip or ductile deformation you can say. What is the nature of deformation in cataclasites? It is the grinding, cataclasis. This is the basic difference. So here the process is called myelinization. Rock is called a myelinite. Follow this point. So in case of myelinite, see, suppose let us take a rock having quartz and feldspar. Suppose you have quartz and you have feldspar. So let us take, this is the parent material. Some biotite made there, this is feldspar. So this is the parent rock. So parent rock generally is named as protolith. इधर प्रोटोलिथ क्या था ना अपना डिपार्टमेंट में, क्या है कि नहीं क्या है? प्रोटोलिथ का मतलब क्या हुआ फिर? तो हमारे पास एक सेकेंड एमएस का लड़का इधर बैठे ना, एक दो तो बैठे हैं, तो वो आके आया बोला प्रोटोलिथ बनाएंगे। प्रोटोलिथ का मतलब क्या है भाई, तो मालूम नहीं था, तो फिर क्या बना रहे हैं? प्रोटोलिथ का मतलब क्या बता? तो बहुत सोच के ओरिजिनल थिंग, यू नो, ओल्ड थिंग्स व्हिच हैज बीन डिफॉर्म्ड, दैट ओल्ड थिंग इज कॉल्ड प्रोटोलिथ। आप एक नया नाम क्यों नहीं देते? प्रोटोलिथ इज द ओल्ड थिंग व्हिच इज रेफर्ड एज प्रोटोलिथ। आप क्यों प्रोटोलिथ नाम देते हैं? न्यूलिथ दे दीजिए। न्यूलिथ दीजिए, न्यू थिंग को आप प्रोटोलिथ देते हैं, इसका सर्वाइवल कितना दिन रहेगा? सो प्रोटोलिथ को अंडरस्टैंड ना, प्रोटोलिथ मींस व्हिच इज सर्वाइव्ड, ओरिजिनल रॉक व्हिच हैज बीन डिफॉर्म्ड। प्रोटो मींस द ओल्ड, फॉलो द प्रोटोजोइक, the oldest rock where life started appearing. That is why it is called protozoic. Archean में there is no life. Protozoic, that is the oldest rock where zoic appeared, life appeared. That's called protozoic. Then comes Paleozoic, little younger. Cenozoic, further younger, you know. So this protolith means the parent rock over which this year zone is given. You understand what is meaning of protolith? And see, you are deforming this rock, quartz and feldspar bearing rock. Spar को अभी छोड़ दो, quartz and feldspar. So here you should understand it. Now quartz and feldspar, suppose this rock is appearing at the surface of the cross section. इधर appear कर. But now we are talking about this level, है कि नहीं? यहाँ हम देखते हैं where a fault will generate here. So quartz and feldspar, these are the two constituents of the protolith, quartz and feldspar. So quartz will behave as a brittle mineral, feldspar will also behave as a brittle mineral. You don't understand this part or not? Tell me, because the rock is brittle, so quartz is brittle, feldspar is brittle. Now you are taking this rock down, you know, from ductile brittle zone to brittle ductile transition zone to ductile zone. So gradually what is happening? Quartz and feldspar are becoming gradually softer. Then ductile deformation will start, or it will remain in the brittle field. Now point is, quartz and feldspar, you think quartz को हम नीचे ले रहे gradually taking down. And feldspar we are taking down. Both of them will not become ductile at the same time. Try to understand this point. Quartz will become ductile at 200 degree centigrade. तो कितना डेप्थ में हो जाएगा? सपोज आप 10 किलोमीटर में अराउंड 300 सपोज लेते हैं, 10 किलोमीटर quartz becomes ductile. But feldspar को ductile करने के लिए you require 15 किलोमीटर. 15 kilometer means how much? Around 400 degree centigrade. You understand this part? At 300 degree centigrade, quartz may become ductile, soft. But to make feldspar ductile, you require still higher temperature, 400 degree centigrade. So this picture, if you take 20 kilometer, then both of them will be ductile. You could understand. So there will be a zone where both of them are brittle. There will be a zone where quartz is ductile, feldspar is brittle. There will be a zone where both quartz and feldspar will be ductile. तो they will behave differently ना, because they are not the same mineral. Quartz को क्या है? Quartz is such a mineral, though it requires very high temperature for melting, but in the presence of water, you know, it becomes very easily, you know, very low temperature, it becomes ductile. Quartz का habit ऐसा है. Quartz is such a mineral which, you know, in presence of water, pH 2, water pressure, it becomes ductile very fast. Even in surface condition, he says, sometimes in surface condition also quartz becomes very ductile. But feldspar is very, water does not help. Either it will alter, or if you want to make it ductile, you know, really you have to take it very deeply. You understand this part? So water is a great role to make the rock ductile. अब ग्रेनाइट कितना में मेल्ट करता है? ग्रेनाइट मेल्ट रिक्वायर्ड टेम्परेचर इट कम्स 700 डिग्री सेंटीग्रेड. 700 डिग्री सेंटीग्रेड में ग्रेनाइट मेल्ट बनता है. अंडरस्टूड ना? For the individual minerals you see in them, quartz and feldspar, quartz melts at 1300, 1400 degree centigrade. Feldspar is also very high temperature it melts, but a granite melt is produced at 700 degree centigrade. How it happens? Because of this. Always remember, during metamorphism, the rocks melt na, in amphibolite phases. But that melt, you know, is because of this pH 2. pH 2 helps melting of the rocks. Even the rock is the mineral, individual minerals, they have very high temperature of melting, but in presence of this water, at low temperature they have firmly melt. That is why quartz becomes ductile at 300 degree centigrade. Now feldspar becomes ductile at 400 degree centigrade. Would you follow this point now? Now हम तो ये discussion करेंगे ना, how a myelonite looks like. We are going to discuss how myelonite looks like. We will discuss in this way. The quartz has become ductile, but feldspar is still brittle. You understand this part now? Why I am bringing this into pictures? We will not take a zone where everything is ductile. We will discuss that. But before that, let us discuss half. Quartz is ductile, feldspar is brittle. वो सबसे मजा देखने के लिए. One is behaving in a brittle manner, another is behaving in a ductile manner. So how a rock looks like? Then we will go to when both of them behave in a ductile manner. Then all features will be lost, you know. Once all of them becomes ductile, they will start flowing. But if one is brittle, one is ductile, this will not flow, this will break like a brittle manner, this will flow, so they will produce very interesting features. Very interesting features. Then that myelonite we will discuss. Where one is ductile, another is brittle. There, if that is the case, you don't understand this part, na? मैं क्या बोल रहा हूँ? So, but that rock will be, there will be some feldspars here and there lying, still survive. Feldspar भी brittle है ना? And quartz has become ductile. There are bendings. So quartz has become ductile quartz. Feldspar is brittle. You don't understand this part. So I can classify myelonite just like the cataclasites, you know. You have protomyelonites, myelonites, and ultramyelonite. You understand my point? I'll repeat, don't worry. Now we can classify a protomyelonite where clasts are 90%. Then myelonite 50%. Ultramyelonite 10%. So suppose somebody asks you, what are these clasts? Clasts are made of feldspar. They are brittle. तो उसमें कितना if clasts are many, then it is a protomyelonite. If clasts are absolutely very, that means feldspar is becoming towards more and more ductile. It is going towards more ductile. Then it is becoming ultramyelonite. Less clasts. If the intermediate number of clasts are there, it is a myelonite. Just like ultra or proto-cataclasites, cataclasites and ultra-cataclasites, we can have three varieties of myelonites. One is protomyelonite, myelonite and ultramyelonite, depending on the class to matrix ratio. So this is class to matrix ratio. है कि नहीं समझा अभी? हाँ? वो कैसे दिखते हैं हम आपको दिखाते हैं, हाउ दे लुक लाइक. So typical myeloid will have a look like this. आपका पास ऐसे सब फेल्डस्पार होंगे. These are quartz. These are quartz. Understood now? This is quartz. What do you say them? Quartz ribbon. Because this is behaved in a ductile manner. So quartz will be stretched, soft. So they will produce quartz ribbons. So this is a matrix part. This is your clast part. So these are feldspar clast. Feldspar clast. Then you have quartz ribbon. Quartz ribbon. Then feldspar clast. Feldspar clast. So these are the features that are present in the myeloid. So you have two basic things. One is a ribbon, another is a clast. So the more the clast, it is a protomyeloid. Gradually the number sizes will be reduced, and you will be getting the ribbons only. Both feldspar ribbon you will get, quartz ribbon you will get. When this becomes ductile, they will be also stretched. Feldspar will be also stretched. So ribbons constitute the matrix. So now you are having two units. One is a ductile unit, another is a brittle unit. So follow this point. So this is a typical look of a myeloid. So you will not get those powders as you see in case of a brittle shear. In case of a cataclassites, these are the areas where you will get the dust. But here there is no dust. They are all ribbons. So now next class what I will show you some typical slides of myeloids. Some pseudoductile slides also I will show you. Then we will discuss different features in a myeloid. Understood? So we will start it here. Next class let us see.